Hello, welcome back, Geometry. This is actually our last section in Mod 6. It goes pretty quick, doesn't it? 6.2, apply sequences of transformations. We've seen a little bit of this before, and now we're going to be able to write formal coordinate rules for them. So learning target today is I can determine the effects of a sequence of transformations on a figure, and success criteria, we're going to be looking at those coordinate rules and make sure that we can represent them graphically and algebraically. Pause if you need to. Okay, first thing, you don't have to write this down. First thing that I want to look at specifically is if you take two transformations, will the order matter? So if you do one transformation first and then the second versus the second and then the first one, right? If you switch the order, are you going to get the same point or not? Let's test it out. First we'll start with rigid motions. Let's pick two translations. I have these vectors 1, -3 and 6, 2. So if we were going to perform these translations on this test point 3, -5, let's change the order. I'm going to do this with a little table just so we can keep things organized. We see that in one table, we're going to do the vector 1, -3 first, and then 6, 2. On the other one, we're going to perform this translation first, 6, 2, and then 1, -3. So taking that test point, let's see if we get the same thing with both orders. 3, -5, so I'm going to add 1 to the x coordinate. I'm going to minus 3 from the y coordinate there. And then I'll take 4, -8, add 6 to it, that gets me 10. Add 2 to it, that gets me a -6. So there is my image point after those two translations. Are we going to get the same thing over here? Let's take our point, 3, -5. This time we'll add 6 and add 2 first. So 6 plus 3 is 9. -5 plus 2 is -3. And then we'll do that last translation there. Check it out. We get the same thing, right? So in this case, when you're doing specifically two translations, order doesn't matter, right? It's still, you're just moving things around, right? Okay, let's check it out with a couple more transformations. What about two reflections? What if we reflect across the y-axis and then reflect across the line y equals x? Or reflect across the line y equals x first and then reflect across the y-axis? I just chose a test point, 1, 3. Is that the same as before? No, it's not. All right, I'm going to do it in two little tables here. So again, let's follow our coordinate rules. So I'm going to take the point 1, 3. First, I'm going to reflect across the y-axis, which just makes your x coordinate negative, so that becomes -1, 3. And then a reflection across the line y equals x. Flip those coordinates around, so 3, -1. All right. Second order, let's flip that order again. First, we will flip the coordinates. That's our reflection across the line y equals x. So this becomes 3, 1. And then make your x coordinate negative. Now the x coordinate's the 3, so making that negative is a -3, 1. Whoa, definitely not the same, especially since we're switching our coordinates with that reflection y equals x. So sometimes it works, doesn't matter what order your transformations happen, especially when we saw those two translations. Sometimes order does matter, right? You'll get two different points in the end, so you have to be careful specifying which order you're going to do these points or do the transformations in, excuse me. Last one, let's just double check, make sure we can do this. What if we do a horizontal compression by a factor of 1/3? Horizontal compression, that means I need to multiply my x coordinate only by 1/3, right? 1/3 is our scale factor there. And rotate 90 degrees clockwise. And I have those rotation rules off to the side. Or we'll rotate 90 degrees clockwise first, and then our horizontal compression by a factor of 1/3. I've got a test point, 9, 4. Let's see what happens. Will the order here matter? So first I'm going to take that point 9, 4, multiply the 1/3, our scale factor, to just the x, so we get that horizontal compression. That gives me 3, 4. And then rotating 90 degrees clockwise, we see that we switch our coordinates around. We make that original x coordinate, which is, now we're taking it from this point, right? So the original x coordinate's not the 9, it's the 3. So that original x coordinate now becomes -3, and those coordinates switch around. Okay. I can kind of see already that things are not going to line up, and order is definitely going to matter here, because if I perform that rotation first, you're going to get 4, -9, and then a horizontal compression is going to be taking that 4, multiplying by a negative, or excuse me, multiplying by 1/3. So 4/3, -9. Yeah, order definitely matters on these ones here. So what we are doing, all of these examples here, to test if order matters, to see that we can perform 2 transformations on points, is what we call composition of transformations. All right? This might be a good little thing. You may want to pause and just paraphrase here. Composition of several transformations included is a new transformation that directly maps a pre-image to the final image after each image is used as a pre-image in the next transformation. Oh my gosh, that's a lot. Let's break it down real quick. So again, we see composition of several transformations. I have an example down here at the bottom. Hopefully that doesn't get in your way too much. So first we start off with the point x, y. That's our pre-image, right? And then we see these little arrows that show our transformations happening. We see the coordinate rules happening with them as well. We get a whole bunch of image points after these transformations. So we take a point x, y. We go to -x, y. So that was a reflection across the y-axis. And then we take that last point, -x, y. We multiply our y-coordinate by 2. All right, so now we have that reflection across the y-axis and a vertical stretch. And then let's take that point now and we'll add 3 to our x-coordinates. So that shows a translation to the right 3 units. So a composition of functions, or excuse me, composition of transformations, all it's going to do is take that original coordinate, our pre-image, our original pre-image, x, y, and just map it directly to our final image point, which was the -3 plus, or the -x plus 3, 2y, right? After all of those transformation happened, the reflection, the stretch, and the translation, we just have going from x, y to -x plus 3, 2y. So that's an example of composition of transformations. Okay, again, we're going to look at composition of transformations here, but I do want to classify all of these. This would be a good thing to have in your notes if you don't have them already. Remember earlier we talked about like this umbrella of transformations. Transformations, anything that changes size, shape, location, etc. of a figure, right? And we classify those transformations as either rigid or non-rigid. So rigid motions were translation, rotation, reflection. They're not changing the size of my figure. They're not changing the shape of my figure. They're just moving things around, right? Our non-rigid motions, we talked about in our last video, dilations, stretch, and compressions. Those are things that are actually going to change the size or shape. Dilation is going to change the size. Stretch and compressions are going to actually change the shape, right? So we can classify these transformations as 2 different types. One thing I want you to keep in mind when we do these compositions of transformations, if you do 2 rigid motions, your composition is still going to be considered a rigid motion because you did 2 rigid motions, right? So if you do a translation and a reflection, okay, your figure, it moved around, but hopefully it didn't change size or shape. If you do a combination of rigid motions and non-rigid motions, let's say you do a translation and a dilation, the end result, your composition, is going to be a non-rigid motion, because as soon as you threw that dilation in there, as soon as you threw that non-rigid motion into your composition of transformations, it definitely changed the size, changed the shape, right? So your end result of a rigid and a non-rigid motion together is going to be a non-rigid motion, all right? Okay. These would be some good examples to get down. I have a couple here that I would encourage you get down just so you see some examples. Consider the transformation rules. xy going to 2x comma 2y. That's a dilation by a factor of 2. And then we have another rule, x comma y going to yx. That is a reflection across the line y equals x, because I see those coordinates being flipped around. So if we had to make a composition of these functions, put them all together, let's say we do our dilation first and then our reflection, what it's going to do is it's going to take a point, xy, and go to 2x, 2y. There's our dilation. Now, let's use this point as our new pre-image point with our reflection here. So according to this reflection, I take a point x, y, and go to y comma x. That just flips your coordinates around, right? So if this is our coordinate, 2x, 2y, flipping those around is just going to be 2y, 2x. So in the end, your composition can be written as xy is going to 2y, 2x, all right? So that shows your dilation and your reflection in one step as one coordinate rule. Pause if you need to. Last example that I have here that we'll go over, again, a good one possibly to just paraphrase real quick. We're going to take a figure, transform it by a dilation centered at the origin with a scale factor of 2, just perform another dilation, and then a translation of 4 units to the right and 3 units down. So what's that going to look like as a composition of functions? Let's just take it a step at a time. So we're going to take a point, x comma y. First, we're going to do our dilation by a scale factor of 2. So that's going to turn into 2x comma 2y. Next step is we'll do a translation 4 units to the right. If I'm moving to the right, that means I'm going to be moving in the positive direction of x, which means take your x coordinate, add 4, and 3 units down, take your y coordinate, subtract 3. So my x coordinate is technically 2x, right? Since we're using this point now as our pre-image. So 2x plus 4, comma, 2y minus 3. There we have our dilation and our translation in one coordinate rule. So altogether, if you put that all together, x comma y is going to 2x plus 4, comma, 2y minus 3. Why is it not, if you look down there, why is it not 2 times x plus 4, comma, 2 times y minus 3? Well, if you see in parentheses, we have the x plus 4 and the y minus 3. That's happening like first, right? Kind of like order of operations. So there is our translation first and then our dilation, all right? So this one shows our dilation first and then our translation, whereas down here with that rule, as soon as I see those parentheses, I see that my translation was done first and then my dilation. You could even check to see if you have the same rule, like does the order matter here? With that one at the bottom here, let's take the 2 in the x coordinate, the 2 times the x plus 4, distributed, right? So that's going to be 2x plus 8. 2x plus 8 is not the same x coordinate as 2x plus 4, right? And if you use distributive property with your y value down there, the 2 times the y plus 3 in parentheses, if you distribute that 2, you're going to get 2y minus 6. Again, not the same as this one here. So we see that order definitely matters with this composition. And we can prove that algebraically just by using distributive property and seeing that these two things aren't the same. Okay, well, not too much to write down. Hopefully you got some examples. I will see you in Blackman 107 to check off some notes and have a little review. Thank you, guys.